Okay, so we're going to talk today about the death of our most massive stars. Just to make sure that we, remember last week we talked about the deaths of small to mid-size to large stars. And so let's just review those cutoffs. I'm going to have clicker questions soon enough with them, but just to review them, what's the minimum mass for a star to exist?
0.08 stars.
0.08 solar masses. And why is that a minimum? Why can't you go any lower? Because you don't have enough gravitational force to cause the high temperatures and pressures necessary for fusion. Okay? Then the next step up was, what is the minimum mass for a star to start fusing helium in the core? 0.5 solar masses. And why was that? Because it was kind of a weird one. During the fusion of hydrogen, it actually reaches the degeneracy for the electrons, and that electron degeneracy pretty much stops the hydrogen fusion. And so it just stops fusing hydrogen to helium. It's done. And what does it become? Becomes a white dwarf. So that would be a helium white dwarf, because it fused hydrogen to helium but didn't fuse helium into anything bigger. What do we call the process of fusing helium? It's got to be on. Process of elimination. Oh man, he's leaving me. What do we call the process of fusing hydrogen? Not one, not two, but three. The triple alpha process. That means it's 3 helium nuclei, because alpha is a symbol used to mean a helium nucleus. And so that helium, the triple alpha process fuses helium into carbon. You have to have 3 helium all basically come together at the same time. That is required because it's not a stable isotope if you just try to merge 2 helium together. Okay, so moving up the scale, we had 0.08, 0.5. What is the minimum mass for a planetary nebula to occur? How many? 1 solar mass. So the sun may or may not become a planetary nebula. Yeah, that's all right. Going up further, what is the minimum mass for a star to have the helium flash? Or excuse me, maximum mass for a star to have the helium flash? 2 solar masses. Above 2 solar masses, it will start fusing helium before it ever reaches electron degeneracy, and it won't then reach electron degeneracy. It'll just smoothly start fusing helium. But less than 2 solar masses, it will become degenerate. That means the electrons can't be compressed anymore before it reaches the temperature and pressure necessary to fuse helium. And then when you finally do get enough compression to fuse helium, the whole thing goes at once. So we've got up to 2. Our next step was, what's the minimum mass for something, or the maximum mass, for something to end up as a white dwarf? It was how many? Okay, 8 solar masses. What is the maximum mass of a white dwarf? 1.4 solar masses. So the mass can be up to 8 solar masses, but only 1.4 for the white dwarf. How do those 2 numbers work together? How's that even possible?
Because the white dwarf's only the core.
Okay, the white dwarf's only the core, and it blows off a lot of mass during the death stages of the star. So when our sun becomes a white dwarf, that white dwarf won't be a 1 solar mass white dwarf. It'll be a smaller mass. What happens if we have a white dwarf with a companion that's given it mass? so that it gets up above 1.4 solar masses? It's like we're preparing for the final exam already, huh?
It explodes.
It explodes in a type 1A supernova. And what's left?
Nothing.
Just a cloud of gas. No, there's no object left, just a cloud of gas.
And the companion.
No. Well, yes, okay, yes. And the companion that gave it the mass, you're right. When you said and the companion, I thought you meant the core. My brain went the wrong direction. Okay, there was one more mass we talked about. What's the upper mass limit for something to become a neutron star?
Like 25.
Okay, the numbers, depending on your source, range between 20 and 40. So he said like 25, 30. I quoted one place that said 25, one that said 29, one that said 20, one that said 40. Right, so somewhere between 20 and 40 solar masses is the maximum to end up as a white dwarf. Or it's not as a white dwarf, as a neutron star. But what were the mass ranges for neutron stars? 1 to 2 solar masses. All neutron stars known are between actually 1.1 solar masses and 2.01 solar masses. So once again, you have to have a lot of mass, 8 to 20 solar masses, or 8 to 40 solar masses, but it ends up with only 2 solar masses as the most massive. What keeps a neutron star from collapsing?
Isn't that the neutron degeneracy?
It's neutron degeneracy. White dwarfs are held up by electron degeneracy. Neutron stars by neutron degeneracy. Now we're going to talk about stars that are more massive than this. So we'll just say over 20 solar masses because of that 20 to 40 range. Up to, what's the maximum mass of a star? 150 solar masses. So now we're going to talk about what happens in the death for a star that's somewhere between 20 to 40 up to 150 solar masses. Reviewed all of the mass things here. A question about got to hit start first. It won't let me ask you the question until I hit start. Okay, this is a question about pulsars, just to make sure we remembered pulsars, which are neutron stars that are rapidly rotating. I'm going to talk about pulsars for like 3 slides here. Why does the pulsar's period decrease over time? We asked this question last class period, so it's not new to you.
Hey, accurate.
Yes.
Since we can only see a small portion of pulsars, doesn't that mean that most neutron stars could be pulsars? We just don't see them?
Well, probably virtually all neutron stars start as pulsars. But because they do slow down over time, they may not be pulsars eventually. But if you are not looking at the right angle, you don't see it as a pulsar, so you just see it as a neutron star. Okay, the breakdown we had where 2 people said it slows as mass is lost, and 10 said it slows as energy is lost. And Daniel.
Okay, so we talked about this last time and you kind of gave an example using, I think this here. Yeah. And you told us this last time. And, you were saying that it slows as energy is lost.
Perfect. He remembered my example with Latifah spinning around and there was friction that made her slow down. And he said it's the same thing. You're going to have something that's going to make it lose mass. In this case, it's losing mass because of the energy that's going out in the pulses. So that was the perfect answer. We talked about these glitches. What caused those glitches according to theory? Those glitches are when it suddenly speeds up.
It contracted.
It contracted. So now, and I think I have this on the next slide, but just to bring it up, as a general rule, over time, pulsars should slow down because they lose energy. When pulsars start, they might have a frequency as much as 1,000 rotations a second, which is incredible. But the very fastest rotating pulsars that have been measured are old pulsars. How can the very fastest pulsars be old pulsars? I could have asked you something like this on the test, but it's a little bit too hard.
I guess they contracted to be so small that they spin really fast.
Okay, one shot would be they contracted to be so small. It's a good thought, but it's not the answer that scientists have come to because of the limited amount of contraction they can undergo. The clue is these very, very fast pulsars that are old pulsars are always found with a companion. What does that suggest? They're getting mass from their companion. As that mass comes in, it's increasing their angular momentum, making them spin up. And so it's one of those apparent contradictions, just like 99 point whatever percent of all meteors are cometary debris, little pieces of dust essentially. But all meteorites are pieces of asteroids. Yeah, it seems like that's contradictory. But the answer was, well, that's because the 99 point whatever percent that's pieces of comets just burns up as it enters the atmosphere. The only stuff that doesn't is that piece of asteroid. Similar thing here. As they get older, they slow down. But if you have a companion, you can spin up. So the very fastest ones are actually old. And so I think I have something here. No, I don't actually. So this is just finishing up the pulsars. Most pulsars emit visible and radio photons. As they slow down, the energy they emit goes to lower energy. So old ones will just be emitting radio waves because it's a lower energy emission. The ones with very high radiation are called X-ray pulsars because X-rays are very high energy, or magnetars. Magnetars, very strong magnetic field. Okay, now questions relating to how I started the lecture here, going through the masses. What size of star becomes a planetary nebula as it dies? Okay. This one was not clean. So we've gone through this. Aldwin, do you remember?
I clicked D.
Okay, well, just tell us what you think.
I B. To 0.08 to 1 solar mass. Because our sun, didn't you say our sun was planetary?
Our sun is right on the limit. So it had to be one of these two because our sun is right on the limit. But our sun is actually the lower limit to become a planetary nebula. So the correct answer here is C.
Yeah, I clicked D by accident.
I'm okay with that. Okay with that. As long as you were thinking, I mean, that's the goal, right? That's why I don't grade you on right or wrong. I grade me on if you're right or wrong, by the way. I go through to assess how well I was teaching by percentage of students getting right answers, but it doesn't reflect on your grade, only on mine. Okay, next one. What size of star becomes a neutron star when it dies? You're right. Now it's open. I'm sorry. Okay. We have all answered. We have, oh no. 4, 6. I can't read the number here, so that's why I had to add the others. Okay, and this one goes to Gabby.
Okay, so I had a couple different answers that were
Bouncing to your head.
I'm pretty sure it's either D or E.
Okay.
And I thought that because D, I was pretty sure you said became a white dwarf, but I could have been wrong about that. And then I was thinking maybe it couldn't be E because you said something about one of those being a neutron star. But then if you had said it, I couldn't remember if you talked about it, but we were talking about it today. So I was thinking we wouldn't have talked about a neutron star if we hadn't talked about it. But I was pretty sure D was a white dwarf, so I'm going with E.
Okay, so she said E. The correct answer was D. D. So this is actually, there's one more that comes up in just a little bit, but this is the last right now. So let's just go through these one last time to look at the boundaries. This lower one is brown dwarves. I put dwarves, not dwarfs. They're failed stars, if you will, not quite big enough to become stars. 0.08 to 1 solar mass. Well, these will be red dwarfs at the bottom side to our sun. Let's just put our sun. And they will end up as white dwarfs without a planetary nebula. 1 to 8 are larger. They will end up as planetary nebulae plus a white dwarf. So that's why there was the divider there at 1. So 0.08 to 8, they all end up as white dwarfs, but it's if it has a planetary nebula or not. Then the 8 to 20 is large stars that will end up as neutron stars. And a type 2 supernova. So you have the supernova remnant. 20 to 150 end up as black holes plus a hypernova. And greater than 150 is too much mass. So there's our limits once again. How do we know all of this? It comes down to that. We have computer models that say that we have these limits. And like there's that discussion if the sun will or won't become a planetary nebula because it's not perfect numbers. But they don't just rely on that. After they've come up with these, then they look out there for stars to try to see. Now, do we see stars like this, like this, like this? You know, it predicts that if it's like this, it should be like this. And so they look for confirmation of the predictions. Because if it's only a computer model, you don't have super big confidence in it. You want to have something that's physical that says, yeah, the computer predicted something reasonable. Now going to black holes. The idea of a black hole was actually first proposed by, I believe it's Thomas More. And what he realized was you have an escape velocity, right? The speed that something has to get away. We've been talking about this on Earth. The escape velocity is 11.2 kilometers per second. And we learned that the equation, and this is actually on the next slide, I think, is V escape is equal to the square root of 2gm over r. Now, what Moore realized was if I have enough mass compacted into a small enough region, then I could conceivably have the escape velocity is equal to the speed of light. And if the escape velocity is equal to the speed of light, that means light can't escape from it. And so Thomas More called this a dark star because it would be a star that we don't see any light coming from. So let's just do his calculation really quickly. C is the speed of light, so we just take this equation and solve it for r. what's the first step you would do, Daniel, to solve this for R? Actually, I shouldn't call him Daniel. I already called him you once today. Jessica, what's the first step you would do to solve this equation here for R? Not super comfortable? Okay. The first step is going to be to square both sides to get rid of the square root. So if I square both sides, I'm going to have 2gm over r is equal to c squared. There's only one step left. Solve that for r by multiplying both sides by r and dividing both sides by c squared. And there's the equation for the radius of a black hole. This radius is called the Schwarzschild radius. And the Schwarzschild radius is the distance out from a mass of mass m where the escape velocity is equal to the speed of light. There's a name for that surface, and it's called the event horizon. So the event horizon, if you have a spherically shaped black hole, is a sphere with a radius equal to the Schwarzschild radius that we just calculated. Now, this is just straight physics theory. If you take mass and you compress the mass, so its radius, you have a mass of m. It could be the mass of Russell. And if I take the mass of Russell, I compress it down to the radius smaller than this, Russell becomes a black hole. Now let's calculate how much I'd have to compress Russell to make him a black hole. So let's approximate, see, G is equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, if I remember right. I didn't look it up, so. And let's approximate Russell's mass is just 100 kilograms. And speed of light is equal to 3 times 10 to the 8 meters per second. Okay, so I put G as 2/3 times 10 to the minus 10. It's the same as 6.67 times 10 to the minus 11. So if we calculate Russell's Schwarzschild radius, 2 times 2/3 times 10 to the minus 10 Newton meter squared per kilogram squared times 10 to the second kilograms, that's his mass, divided by 3 times 10 to the 8th meters per second, quantity squared. So if you go through and do your math, first let's just do the numbers. 2/3 times 2 is 4/3, right? And 4/3 divided by 3 squared, or in other words, divided by 9, would be 4/27. And then looking at our powers, 10 to the minus 10 plus 2, so 10 to the minus 8. 10 to the 8th squared is 16, so minus 8 minus 16 is minus 24. And my units here are going to be (2gm). Oh yes, there's a kilogram in Newton. I was like, I'm not canceling everything right. Meters. So 4 out of 27. With it's a good approximation. 27 is 25. That's a good approximation. And so if I multiply top and bottom by 4, I'd have 16 over 100, 0.16. So this is approximately equal to 1.6 times 10 to the minus 25 meters. What was this calculation? It was the Schwarzschild radius of Russell. So if we crush Russell so that he has a radius that's about 10 to the minus 25th meters, Russell would become a black hole. How could we crush Russell to be that small? It is simply not possible. Right? We can't do that. The only way we could do that would be to toss him into a pre-existing black hole. So there's no force that could crush him to that. So we don't have to worry about Russell becoming a black hole. Unless, of course, God works in him. But he won't. So there's no lower limit to the mass of a black hole. But there is a lower limit to the mass that can become a black hole naturally. Right? We could make Russell into a black hole if we had enough force, but we can't get there. But nature can make things into a black hole if you have a mass at depth that's somewhere over 2 solar masses. So there is a lower limit for the mass of a star that will make a black hole, but no lower limit for the mass of a black hole. Now let's go a little bit further. If Russell was crushed to become a black hole, he's a black hole, he still has the same mass. How would that affect Hannah? She cried?
She died.
Oh, John. I mean, because we probably cried to see him crushed in front of us, right? The fact is, his mass would be the same, their separation's the same. She's going to have the same attraction to him by gravity that she does now. You don't feel yourself being pulled over, right? So she wouldn't be pulled into him. He would have the same force to her. He wouldn't be pulled into her. But he would also have the same attraction to the center of the earth. And he would be much smaller than the separation between atoms in his chair. So he would fall right through his chair, right through the floor toward the center of the earth. And what would happen if some atom got inside of the Schwarzschild radius? Remember, the force of gravity is stronger as soon as you get closer, and once you get inside the Schwarzschild radius, nothing can get out. So as he falls to the earth, he's going to eventually, hit an atom, and what happens then? Yeah, that atom becomes part of the black hole. And so as he falls to the center of the earth, his mass would grow. When he gets into the liquid core, he would almost certainly start picking up more mass, probably have enough mass that eventually he would gobble up the core of the earth. We would have an empty core with a black hole in there bouncing around. Okay, I say bouncing around, it would actually be going, as it grows, well, that can be a problem. But if it just stayed in the center of the earth, if we had a black hole in the center of the earth and it was just stable in the center, there's only really one difference it would make for us. That difference is we wouldn't have our magnetic field because we need that liquid core swirling around. But none of this is ever going to happen because it's not possible for any of us to be crushed into black holes. But it's kind of fun to talk about the black hole idea because people just assume, black hole, it's going to pull everything in. If the sun were... Excuse me?
Or it's going to appear from nowhere.
Oh, it's going to appear from nowhere. I've watched enough sci-fi to know. If the sun were somehow made to a black hole, once again, the sun can't just become a black hole. The Schwarzschild radius for the sun is somewhere in the ballpark of, I think, 3 meters. Something would have to crush it to 3 meters and nothing can. But if the sun were to become a black hole, how would that affect life on Earth?
Well, other than we freeze.
We need its light, we need its heat, we need its energy. That's what would change. That's the only thing that would change. We wouldn't get any light or energy and we'd freeze. But we wouldn't get suddenly yanked in. Sorry, something in my eye. Now, Einstein, with his theory of relativity, which is what this was focusing on, said that mass, instead of making a black hole like Moore had suggested, that mass warps the space-time continuum. So these pictures are supposed to try to give us an idea of what it would mean to warp the space-time continuum. So that picture there says, imagine that your bed surface is a 4-dimensional sheet. How many people are good with thinking about a 4-dimensional sheet?
Right.
Okay, I'm really good with 2 dimensions because that's what the bedspread really is. It's 2 dimensions. But we live in a 4-dimensional world. We have 3 dimensions of space, 1, 2, 3, all perpendicular, and we have 1 dimension of time. And the fabric of space-time we live in is that 4 dimensions. And according to Einstein, a large mass will warp that 4-dimensional space. So you can't take this bed analogy and say it's correct, but it's an analogy to help us understand. With a 2-dimensional surface, if I put a bowling ball on the bed deforms or warps because of the bowling ball being there. And so the heavier the ball, the more it's going to deform, right? And that's the same thing with gravitation. The bigger the mass, the more it deforms the space-time continuum. And if you have enough mass, it will deform the space-time continuum. So the space-time continuum forms an enclosed sphere. So if you're inside, you're essentially in a different time and space. And you can never get out because the space is now closed on itself. So you could travel any direction you wanted, and you can't get out of the black hole, just because the space now is closed on itself. So that's the Einstein understanding of a black hole. Okay, here's my nutty theory. As we'll see in a little bit, there are the same types of things at different sizes in the universe. And I really like the idea that our universe is inside a black hole. And so that would explain dark energy. Dark energy, scientists have determined that 70-odd% of the universe is some source of energy that they have no knowledge of. So they call it dark energy. 20-some% of the universe is mass that we have no idea about. So they call that dark mass. It comes down to just 4% of the universe is stuff that we know about. Which, if you think about it, that's a really crazy statement about our ignorance.
But even then, it can be disproven.
But everything we know about, the Earth, the Sun, the solar system, all of the stars, all of the gas out there, that's only 4% of what's out there. Everything else we have no clue what it is, so that's why they have the term dark. Dark mass, dark energy means we don't know what it is. Well, I like to think we're inside a black hole, and so when that black hole has material fall in, well, then there's more mass, and that's the source of the dark energy. Right? It makes some sense, and I'm not the only one who's come up with this idea I've seen, but it's a cool idea. And we can't say what the laws of physics would be inside of the black hole, so who knows? All right. I have this equation here because I was going to do the derivation. We have that the masses of stars that will form black holes are somewhere between 20 to 40 on the minimum, up to 150 solar masses on the maximum. Of the black holes that have been identified, of course, just the idea of how do you identify a black hole is a good question.
Can't see it.
The most massive stellar black hole, that means a black hole that started out as a star, is 62 solar masses. The least massive is 5 solar masses. So once again, we're looking at, they lose a lot of mass as they're dying, but then they can gain mass after they have died and become a black hole. One of the interesting things to note here on the warping of the space-time continuum is that if something comes close to a black hole, even close to a massive object like our sun, the sun has enough mass that it warps the space-time continuum. So light from a star beyond the sun, when it comes past the sun, it actually changes direction because the space-time continuum has been curved there. So in things like next year, we're going to have that solar eclipse visible here in Lincoln. During solar eclipses, scientists will look and see the same star on both sides of the sun, or maybe even 4 different places around the sun. And the only way that can happen is if the light from that star is coming out, spreading in all directions. So you have light from the star is going, like this, and like shown there. But then, because of the warping of space, it changes direction. It goes around the sun. And so if you are standing here, you see the star coming from that direction as well as its light from the same star coming from that direction. So you see the star in multiple places because of the warping of the space-time continuum. And I just love to say warping the space-time continuum. Now, while I'm saying warp a lot, we've probably all watched one too many sci-fi movies, and we know all about warp drives, right? Whether it's Spaceballs or Star Wars or whatever you've watched, they've got a warp drive. Let's not even use Spaceball. They don't try to be scientific there. There are real scientists trying to work on the concept of a warp drive, believe it or not. Based on what I've said today, what do you suppose a warp drive means?
I always just thought it was an ASTR bridge.
No. That would be an advanced thought, but that's not what it is.
Crazy.
No, you're not crazy.
Maybe it like would change like the rate of time passes or something, so like you could theoretically travel to places really far away and not that much time will pass.
It's actually a little different, and I'll use your notes as an example. Once again, imagine that this is our four-dimensional space-time. If you warp it, you can bend it like this, and if you warp it enough, you can get it so the paper's touching. Now, you have one four-dimensional space-time where my right middle finger is, and one four-dimensional space-time where my left middle finger is. If you can bring them so they're right next to each other, and then you can find a way to tunnel between the two, then you will have moved the distance equal to the separation of my fingers here with virtually no actual motion because you warped two spaces next to each other and then you jumped across it.
That's what I thought it meant.
It's
A little different.
Yeah. So that's the idea of a warp drive. And there are real scientists trying to work on this. Now, do people think it's likely that they'll ever come up with this? No. But theoretically, is there a possibility? Yeah. And so that's why they spend time trying to figure it out. Because, if we can figure out the warp drives, then, Star Wars is no longer fiction. We can be like Star Trek and go, space the final frontier. Okay, moving on.
Let's assume there's something out there. So you just get trapped in that place else to go.
There's going to be stars at the very least.
Yeah.
Some planets.
How do you get that?
You use a warp drive to reverse.
And then you have to make it portable so you can bring it onto the spaceship. Because thinking about it, not that.
What is the minimum mass for a black hole? Tony, Jessica, and Russell.
And then again, you can never tell if it was successful because how you can radio back. You have to think of some futuristic radio message.
You're spending too much time on this.
I just like thinking apart theories. Sorry.
If you talk about tachyons, you come up with interesting things. It can be shown that if you communicate via tachyons, which are particles go faster than the speed of light, you can tell somebody before it's happened what's going to happen, but they can never respond in time. Okay, so we had a pretty strong agreement here that 20 solar masses was the upper limit for a black hole. And that's wrong. Or excuse me, minimum. Yeah, minimum. Excuse me, minimum. You're right. But that's wrong. So clearly it wouldn't be worth our time to ask somebody to explain. So talk to your friends and neighbors about the minimum mass for a black hole. Notice the wording. It doesn't say the minimum mass for a star to become a black hole. It says the minimum mass for a black hole.
Oh my gosh. There's no minimum. It's not asking for a star because if you become a black hole, you just have to experience it, like you just said.
You should have a star.
So it was a trick question the whole time.
It kind of was.
Yeah.
Okay, so
It kind of was a trick question. It was a trick question. In the dictionary, when they have an example, this is the question.
No, this is not in the dictionary. This is a straightforward question. It's just not what you had as your preconceived what he's going to ask.
It's kind of like
So-
how you're putting on the test. What's the closest star to Earth? The
Yes.
sun.
Yes. And I try not to, because that question gets written down because you forget the sun, right?
Yeah. You're talking about approximate.
So that's right. Not just alpha, proximate. Unless it says visible. Okay, answer again the people who haven't.
Believe that the sun is a star, right?
What?
You know, there's some people that don't believe the sun is a star, right?
I suppose. I don't know.
You see, this is what your American education system is for.
Don't be bad-mouthing my American educational system. Okay, Aldwin, Russell, and Jessica.
Yeah.
Answer again, please.
There is no minimum.
No, on the clicker.
There is no minimum. There's no minimum.
Okay. Man, I really feel like I should call on Aldwin, but Tioni's card came up.
Dang it. I'm ready.
Second time around.
Put me in coach.
Second time around.
I could finally bring the Raiders to the Super Bowl. Put me in coach.
Tioni, what'd you answer? Give us our reasoning here.
Well, you didn't specify if it's for a star, so I just assumed there is no minimum.
That's right. There is no minimum for a black hole, but for a star to become one, there is. And the one that people answered, the 20 solar masses, or 20 to 40, I don't know, somewhere in that range, would have been the right answer if it had said for a star to become a black hole. And these three people should have more faith in Aldwin.
Gosh, guys, I yelled at you 8 times. 8 times before we even answer the question.
Okay, moving on. So I talked about seeing a black hole. How do you see something that's not emitting any light?
You see
You measure the
you
effects
see
of
the
it.
stuff around it.
Okay, you see the stuff around you. You measure the effects it's having on things around it. So a black hole, by its definition, no light comes out. And you can't just look for a region where you don't see anything. That's not the definition of a black hole, right? Because there could be nothing there. But a black hole has to have a lot of mass. And so you're going to see things orbiting around that. And so when the black hole forms, it's going to have an accretion disk. It's going to have this disk around it. Now, this picture is showing when it has a companion star, but even if it doesn't have a companion star, it's going to have a disk around it. And that material in the disk, over time, it will fall in. Whenever any mass falls in, you're going to have a bipolar jet, charged particle, because the magnetic field is being directed out. And so you see those jets as well. So you have the accretion disk to look for. If you find the accretion disk, you measure the time that it takes something to orbit around and its distance from the center.
So light can escape.
Those two pieces of information would tell you about the mass of the center. No, light can't escape. There's no light that comes out from what's inside.
But it can get away from you. Theoretically?
That's it.
Can light escape at the white hole theoretically?
When you have the Einstein-Rosen bridge, yes.
So you can see a white hole.
Yeah, hence the change in name. But those are not known to exist. They're theoretical.
That's why I said theoretically.
Okay, what were you asking, Russell?
No, but I mean, the light around it can escape.
Light around it could escape, yes. What's going to happen to that light is it's going to lose energy. So if you had something that was super, super hot, something that's giving off, blue light or X-rays, as it tries to escape, it's going to lose energy and it'll come out redshifted. So you have a gravitational redshift there.
So if you were looking at it, you wouldn't necessarily see nothing. You would see like a light trying to escape around it.
You would see the light, like this picture illustrates. Here in the center is the black hole, and you see nothing coming from there. But you can see the material that's outside of it. Now, one last thing to put in here. You may have heard about Stephen Hawking. He's done a lot of research on, theoretical research, on black holes. And one of the things he's talked about is, can a black hole ever dissipate? If not even light can escape, then it should dissipate, right? It should be able to hold all of its mass. But quantum physics is a funny thing. Quantum physics says that even though you don't have enough energy to get out, it's possible for energy to get out. And so
like, why does it quantum physics care about physics at all?
let's not worry about it. We'll focus on this. So if you had a black hole that was isolated, nothing around it, in theory, over a very, 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 very long time,
Like a
It could-
white dwarf cooling down.
longer than that, it could dissipate its energy through tunneling until it becomes no longer a black hole. But you know what? For a class like this, we don't worry about that. That's a really thin chance occurrence. So as far as we're concerned, we'll say once a black hole, always a black hole. It can only grow. Excuse me?
Could you hit it with a shockwave to make it release energy?
No, you couldn't. Okay, so this is just a picture showing, things about observation of black holes. Just pass that by. We're going to end today by talking about clusters. So this picture here is one of the items that you must point out on your lab final. When's the lab final? Tomorrow night. Unless I've got forms at home tonight. If it's clear, you can give me a call. We can go out tonight, and then you can come tomorrow and get extra credit. Or not extra credit, but make up a lab. So this here is the Pleiades. I don't know why I'm writing on it. The Pleiades are the seven sisters, or Subaru. Yep. And so it's an open cluster. It's a cluster of stars that were all formed from the same cloud at the same time. An open cluster can spread out even further and become an association. And let's just look at some definitions here. Open clusters contain just a few thousand stars. So, 5,000 stars, 10,000 stars. And they're about 14 to 40 light years across. Now, I say a light year is a big distance, right? So I think that's a big distance. But if we compare that to a globular cluster has millions of stars and has a volume that's spread across 80 to 320 light years. So globular clusters are much bigger and have many more stars. When you look at them, can you tell the difference in the open cluster versus the globular cluster?
Yeah, you can see it.
Pretty obvious. The globular cluster is very clearly a cluster. The stars are clustered together in a glob. Why? Because you have so many stars, so much mass that the mass is holding them tightly, so they're not getting away from each other. Open clusters have less mass, which means that they can spread out more, and you don't see that tight cluster. Now, when you look at the stars, let's look at this picture. What color stands out to you?
Red.
Red. If you see red, what are you seeing? You're seeing cooler stars. So you're not seeing massive stars, you're seeing lower mass stars. Things like red giants. They're bright, so they must be a giant. So you're seeing older stars or smaller stars that have died, which means this has to be really old because smaller stars live a long lifetime. If you look at, this one here has,
Are usually smaller stars more massive?
no, the smaller stars are less massive. This one here has some red, but it has a lot of blue. A lot of blue would be hot stars, more massive stars. They have short lifetimes. So this one must be younger because it has a lot of blue. This one older because it doesn't have a lot of blue. So you can tell something about the age just by looking at the colors of them. A summary of the clusters. Open cluster has, tens to a few thousand stars. I think that's slightly different than what I had in the previous slide for the size, but much smaller in size, much fewer stars. Globular clusters, 100,000 to 1 million is what I have here. Size of 60 light years. Associations, 50 to 70 O and B stars. What's an O or a B star? Those are very hot, which means they must be what in terms of mass? They must be very massive stars. So it has 5 to 70 very massive stars. This doesn't say how many less massive stars, just how many massive stars that have spread out over a large distance. What's the usefulness of these? The usefulness is when you find a cluster of stars, that cluster of stars all form from the same cloud at the same time. If they all form from the same cloud at the same time, how do we know they form from the same cloud at the same time? There are really two ways of analyzing. One is to try to measure the composition as best you can and compare the compositions. But the other one is looking at our theory of star formation. If our theory of star formation is correct, that you have a big cloud and you have a shock wave that goes through, then you should have lots of stars form at once. And so you should find stars that are groups of stars that all formed at once. And so it holds together theoretically, but there is a measurement to try to determine it. If you take all the stars in a cluster and you plot them on the HR diagram, you're going to see what the HR diagram looks like for a certain time. And so for every mass, you're going to see where that specific mass is on the HR diagram at this age. And so this picture is showing where you find stars on a specific cluster. What stage are these 4 stars in right there? They're still forming. And so we can say, aha, here is where they reach the birth line. If I know how long it takes for a star to form, then I can determine the age of the cluster just by looking there. But there's a second one for measurement, because what's going on right here? They're dying. They're leaving the main sequence. And so if we know, given this mass, it should spend this amount of time on the main sequence, which we have a much better handle on, then we can say, the age of this cluster is blank based on the mass where it's leaving the main sequence. We call that the turnoff point, as you see right there, the turnoff point. And so that's how you actually determine the age, is by finding the turnoff point, which allows you then to use this here to determine how long it takes for a star to be born. And then you can see, what's happened here. You don't even see any stars in that middle region, but you have the shell burning out, right? So that's what's caused that rapid move over to the giants. And you don't have any white dwarfs here, not old enough for them to have formed yet. Okay, we're out of time. I'll see you tomorrow.